Welcome to The Explainer. Today, we're going to pull back the curtain on policy gradients. These are the really powerful algorithms that basically teach AI models how to teach themselves to get better.
So here's the plan. We'll kick things off with the basic idea of how an AI even learns in the first place. Then we'll walk through three super important algorithms: reinforce, PPO, and GRPO. After that, we'll put them side by side and finally talk about why any of this actually matters.
So how does an AI model actually get better at something? Let's start right at the beginning with the fundamental principle of learning from feedback. At its very core, it's all about trial and error. The model makes these tiny little adjustments based on whether an action led to a good result or a bad one. But it's not random. It does this in a really structured way.
And the way this is done is with a fundamental rule called the policy gradient. You can think of it like a mathematical recipe. It literally tells the model exactly how to update its own internal wiring, what we call its policy, so it can get better results the next time around. This update rule is actually pretty simple. It's got two parts. First, the AI figures out which of its internal knobs to turn to make a certain action more likely to happen again. And second, it decides how much to turn those knobs, and that's based entirely on how good the result was. So if the outcome was fantastic, that knob gets a big turn. If it was terrible, it gets turned in the opposite direction.
All right, first up is an algorithm called reinforce. This is the classic, the OG of policy gradients. It's the most direct and simple way to apply that core update rule we just talked about. So a good way to think about reinforce is like this. Imagine an AI finishes a task, and all it gets is one single score at the very end, basically a thumbs up or a thumbs down. The feedback is super direct, sure, but it doesn't have a lot of detail, and that can make the whole learning process, well, a little chaotic. Reinforce looks at the total reward for a whole sequence of actions. But because that feedback is so simple, it suffers from something called high variance. All that means is the updates can be really noisy and unstable. To try and fix this, it uses a baseline. You can think of it like an average score, which helps it judge if an outcome was just kind of okay, or if it was genuinely great or truly awful. Now, that instability problem with reinforce, it was a big deal. It led researchers to develop a much more advanced and way more stable solution, proximal policy optimization, or as everyone calls it, PPO. The best analogy for PPO is a really cautious golf coach. They want you to get better, for sure, but they will not let you completely change your swing after one bad shot. Why? Because that could make things way, way worse. Instead, the coach encourages small, careful, controlled adjustments. And that, right there, is the whole philosophy behind PPO. PPO gets this stability by using a really clever trick called the policy ratio. It's just a way to measure how much the AI's strategy is changing from one update to the next. If the AI tries to change too much, too fast, PPO basically puts on the brakes and says, whoa, let's slow down. The key mechanism here is something called clipping. See, PPO works on the idea that the old policy it has is probably not that bad. So it only allows the new, updated policy to be a little bit different. This creates what's called a trust region, which acts like a safety rail, stopping the AI from making huge, wild changes that could just delete all the progress it's made. So let's break that down. If an action was good, right, PPO says, yeah, let's do more of that. But, and this is the key part, it clips the update so the AI doesn't get too aggressive. And on the flip side, if an action was bad, it says, okay, let's back off from that. But it also clips that update so it doesn't just completely give up on trying similar things. It's all about finding that perfect, stable middle ground. But PPO has another secret weapon. It actually uses a second, whole other model called a value function. This thing acts like an expert critic. So instead of just getting one score for the entire task, the value function gives detailed feedback for every single step, or in language models for every single word or token. This makes the learning way more precise, but it definitely comes at a cost. It adds a ton of complexity and uses a lot more memory. But what if you could get all that stability without the extra baggage? Well, that brings us to our next algorithm, Group Relative Policy Optimization, or GRPO. The analogy here is all about relative performance. Think about a chef in a cooking competition. They don't need some perfect universal recipe from a book to know if they're getting better. They just need to know which of their own attempts was the best one. They create their own standard right there on the spot. And that is exactly what GRPO does.
For just one prompt, it will generate a whole group of different answers. Then, it figures out the advantage for each one simply by comparing its score to the average score of that group. It's a really clever way to get a high-quality baseline on the fly, and it still uses that same PPO clipping trick for stability.
So the big takeaway here is efficiency. GRPO gives you a lot of the same stability benefits of PPO, but without the massive cost of training and running a whole extra model like that value function. It's just a much more streamlined and resource-friendly way to do things. All right, we've gone through all three. Now let's really put them head to head to see how they stack up. Okay, this table really lays it all out. You can see the whole story here. You start with reinforce, super simple, low memory, low complexity, but it's just not stable. So then comes PPO, which totally nails the stability problem using that learned value function. But look at the cost, high memory, high complexity. It's a bit of a beast. And then you've got GRPO, which is kind of the Goldilocks solution, right? It gets that PPO style stability, but does it with low memory because it ditches the whole extra model. It's a really smart compromise.
So after all that theory, why should any of us really care about the differences between these algorithms?
Because these are the engines running under the hood of the AI that you and I interact with every single day. When a big language model is fine-tuned to be more helpful and less harmful, that's very often PPO doing the work. When a robot learns how to pick up an object without crushing it, that's a policy gradient algorithm. The choice between these directly impacts how safe, how reliable, and just how capable these incredibly powerful systems become.
You know, the journey from the simple, kind of shaky reinforce to the more sophisticated PPO and the efficient GRPO, it shows a really clear trend towards more stable and smarter ways of learning. This ongoing search for better algorithms is honestly one of the most exciting frontiers in all of AI. And it leaves us with one last question to think about. What's going to be the next big breakthrough in how we teach machines how to learn?